Anyone know what an amorphous solid is besides Paul?
Guess not.
Does it morph? Oh no, don't go down that path. No.
I just have to say, do you need a stool?
Okay. There it is. So this is a regular crystalline solid, it's called. That's like salt. That's copper. All the metals up there, this stainless steel. Most solids that you come in contact with are basically like this. This is another type of solid that's very similar to this, but what do you notice?
It's like it's not in order.
It's a little bit cockeyed, right? So like this, it kind of starting to break a little. Which one do you think is weaker?
That one, the middle.
The one that's broken a little bit, right? And then this, how's that different?
It looks like a liquid.
Almost looks like a liquid, but it's not. Why? There's spaces and it's not as organized, right? That's an amorphous solid. So it's almost better to show you than give you a definition. The definition is it's a solid that isn't as regular and repeating. There's spaces in the crystal structures. I have a definition written down somewhere, I'm sure. Particles are arranged in a random formation. Particles are arranged in random formation. It's not as regular or repeating as a regular solid like over here. So those are great examples. I believe the middle one's called polycrystalline.
Isn't that glass?
Yeah, it's in between kind of. But this one, polycrystalline, means you might have groups of atoms that form regular patterns, but then there's spaces between other groups. Sulfur falls in this category between amorphous and polycrystalline. Polycrystalline is not a thing or a word you need to know in the regions. Even amorphous is a little bit of a stretch, but it's part of chemistry. I think I should talk about it briefly. Question?
Jello.
Yeah, Jello is more of a colloid that has solidified. It's a type of solution.
Where did
So-
that come from? I like zoned out and all I heard was Jello.
Jello. So Jello, and so okay, kids always ask this question. So when you think of a solid like this, you think of something like this,
Yeah.
or like this, right? Okay. Well, think about solids that are softer or pliable. Jello's a great example. What?
A pencil.
Wait, is slime
You know, like
liquid
sponge?
or
The particles that make up a sponge.
Like
Fair
those
enough.
good
What else?
It's a solid.
Oh, it's
Rubber. Great one. Rubber is an amorphous solid. Rubber is flexible because there's spaces in the particles. Good. What else?
Oh, my
Steak.
gum that I'm doing.
Oh yeah.
Gum.
Sorry, is that
Roads are made out of it.
Asphalt.
Asphalt.
I'm going to say pavement.
Put a little star here. Glass is complicated. It's not regular crystalline like the one on the left. It's more a combination of these two. There's like 400 different types of glass or more. I wrote it down somewhere. There's maybe 800. There's a ton of different types of glass. All glass basically has silicon dioxide, which is one of the most prevalent compounds on the planet. Silicon and oxygen are two most abundant elements on the planet. That's every grain of sand on the planet, SiO2. That's what sand is. So that's what glass is made out of. But you can add things to it. All right, glass. There's fiberglass. There's bulletproof glass. There's regular glass like this. But this glass is probably a little more sturdy than glass windows in my house. And so there's shatterproof. There's all types of different glass, right? Stained glass windows. There's thick, thin, whatever. I'm not an expert, but there's different types of glass, and that's because when they make it, it starts doing this. So silicon dioxide and minerals and rocks that have those elements and compounds in it can be fairly regular, but once it's melted and formed in the glass and manipulated, it kind of alters it a little bit, kind of like the sulfur. We changed it when we melted it and froze it very quickly. So anyways, these are just solids that aren't as regular or crystalline. They're typically not as strong, right, like a piece of glass or steel. Steel looks like this. There's a piece of glass. I think you get the concept there. However, it's complicated. In chemistry, it isn't always about like strength, like holding something up or breaking. It's about melting points, boiling points, freezing points. So you can have something that might be brittle, but it might have a higher melting point than something that isn't. So I know I'm kind of maybe rambling a little, but the point is amorphous are typically a little weaker than crystalline just because of those spaces. All right? And that was it. I'm glad I looked at my notes. I don't always do that. But that's the only thing we haven't talked about with solids. All right, moving on. We'll talk more about solids down the road in lab. All right, back to table I. So, table I. What'd you learn about table I so far?
I don't remember.
Yes. This reaction gives off 890.4 kilojoules. You don't really know what that means too much. Banana has 400 joules. This has 890,000
Is that
joules.
energy?
Yep, it's energy. So if you burn a banana, it'll give off 400 joules. If you burn methane and oxygen, it'll give off 890,000 joules. Big difference, okay? People burn methane to heat their house. You don't burn bananas to heat your house, okay? You would need millions of bananas for the winter. Millions, okay? It wouldn't work. So that's why we burn natural gas. Yes?
Why is it negative?
Negative, all that means is it's being released into the environment. Exothermic. If it's positive, the ones down here, that means it's being absorbed by the reaction. So this reaction, N2 plus 2O2 yields 2NO2, it needs to take in 66.4 kilojoules in order to react. So all the ones with negatives, they react, give off heat. That feels hot to us. All the ones that are positive, they can't react unless they absorb energy first, and they feel cold to us because they take our energy away. Endothermic, they absorb it. So that's what we already learned. I hope now everyone's like, okay, I remember that. Hope so. Now what we're going to do, only one simple thing here, is we're going to learn how to write these equations on paper. Now what does that mean? So in our notes, let's title this Heat and Energy, because we're going to start learning how to do some calculations with these numbers tomorrow, because I'm running out of time, but that's fine. This is all I wanted to get to today, so we're actually on schedule. So heat and energy. So on reference table I, we know if it's a negative delta H, so delta H up at the top here stands for change in heat. That stands for change in heat. And when there's a negative change, that means energy is lost. If there's a positive change, energy is gained. Think about money. If you lose money, that's a negative thing. If you gain money, that's a positive thing. So think of that. That might help. So anyways, what we're going to do is we're going to take these reactions and just simply write them in our notes. You might think, well, that's easy. I'm just going to copy down what I see. You're right. However, this number, these numbers, have a certain side of the arrow that they must be written on. In other words, if it's a negative or a positive, we write it on the left side of the arrow, or we write it on the right side. And I'm hoping in the next 5 minutes here, we practice enough that you get it and it makes sense, and then homework you're going to practice. That's what that worksheet's practicing. So I'll do the first couple with you here. So let's write this down. CH4 plus, we're going to do the first one, 2O2 yields CO2 plus 2H2O. Just write that reaction down. Then we'll pick a positive. So that's going to be the negative. I'm just going to scroll and you guys have it in front of you. So I'll take the first positive, which is the N2 plus O2. So we have N2 plus O2 yields 2NO. Okay. Now, what's the first two letters of endothermic? EN. What's the first two letters of exothermic?
Yes.
EX. Good. Here we go. Ready? I'm going to lead you to water.
Because we're all horses.
Wait, what?
You're supposed to know.
You did it yesterday.
Oh, nay, I wasn't I'm listening.
So, when do you enter this room?
When the bell rings.
When-
In relation to this class, when do you enter this
When it
room?
begins.
When class starts.
You enter, stay with me, you enter in the beginning of class,
I said that.
right?
Okay, yeah.
Okay, does everyone agree?
C.
Bridget, with me?
And you
When do you exit this room?
When it's
At the
not-
end of class. So you enter in the beginning,
That's so
enter is
smart.
EN, you exit at the end, that's EX. So, who's drinking?
I got it.
The horse
Sounds
is.
inappropriate. Right.
the negative one, you're gonna have the number at the end of it.
The negative number, it will go at the end. Very good. And
The positive one will be at the beginning.
positive will be at the beginning. Very good. Now before you write it, is this number exo or endothermic here? Entering or exiting? Exiting, negative, right? So we put that.
I don't understand.
Wait, why did I'm so.
Alright, hold it, let's back up. Some of us are still thirsty. So 2 steps to answering these questions or figuring this out. First step, find the reaction on the chart, determine if it's negative or positive, and then what does that mean? So negative means exothermic. You don't have to memorize. At the very bottom of the chart, it tells you. Minus sign indicates exothermic. Then you find another reaction, and you say, okay, it's positive. What does that mean? It's endothermic. So that's on you. You need to know how to do that.
I got it.
Then take the analogy. Endo, enter at the beginning.
Yeah.
Exit, exo at the end. So I take I'll start here, positive 182.6, and I write it right here because it enters when it's endothermic. So that's 182.6 kilojoules goes on the left side of this equation, or the beginning. And that makes tons of sense if you understand what I'm saying. This reaction cannot react without that. So you have to give it up front. You have to give it the money up front or else it won't do the job. Alright? So whatever analogy helps, but enter in the beginning, and I think that should help you guys figure out where to put it. Now, the only trick with the exothermic here, you exit at the end. This is what kids get confused about, is this right here. So the only thing I can tell you is when you write chemical reactions on paper, negative signs are never shown. Never. This plus sign is not a plus sign, it just means it's part of the products. So you have CO2 and H2O and 890.4. So all 3 of these are kind of like part of the product side. So that's why we put that plus, but it isn't a plus. This isn't a plus sign. It just means these 2 are together. So that's the tricky part. Kids want to put negatives up here, don't do that. So when you see an exothermic, it goes on the end, you exit at the end, but you cannot put the negative in the equation. That's important to remember. Everybody with me? Okay, let's try one more. I'll write the reaction down, you write it, and then that'll be it. Your homework is practicing exactly this. N2 plus 3H2 yields 2NH3. So write that down and put the energy on the correct side. Is it an exothermic reaction meaning releasing? Is it endothermic meaning absorbing? Entering, exit.
Wait, where is it on the graph?
It's up. It's there. It's up here.
You can point it. I found it.
You're so. Why do you have the windows open?
It's 1,000 degrees.
It's
1,000.
It is really
My
hot.
thermometer blew up. It was so hot.
It is like.
I was sitting here and I just get cold air.
I'm
on my
wearing
feet.
cufflinks again, so I can't roll up my sleeves, so I'm hot.
So why don't you take
Well,
off
that's
the
why I
cufflinks?
should-
Put 'em in
Well,
the
because then it
cufflinks.
gets these shirts. Do you know how these shirts are?
Yeah.
It's awkward. It doesn't really stay up. It flops.
I
around.
don't know how those shirts are. I
At
really
least
don't.
not
I don't
mine.
walk around with buttons.
Where's the 91.8 go?
In the
At
front.
the end.
At the end.
Exiting.
Oh,
It's
boy.
exothermic.
I understand it now.
The worksheet. Do it, Palmer, please.
I understand.
Morgan.
Yeah, I get it. You enter and then the exit and then.